Hi everybody and welcome to my presentation of Cppless, a single source programming model for high performance serverless. Let's give you an overview first. The goal of Cppless is to provide a new way to interact with serverless functions, lowering the barrier of entry and providing a performant and elegant interface. This is made possible through language extensions making transparent offloading possible. And we also provide both a user space library, which makes use of these language extensions, and we integrate into existing compilation workflows through CMake. Currently, the reference implementation supports both a local dispatcher, which executes task invocations locally, and an AWS dispatcher, which executes tasks in AWS Lambda. We strive to be as performant and extensible as possible, and support for other serverless providers can be added by users and is quite easy. Only minimal requirements are put on the serverless provider, and thus we think that a lot of serverless providers could be integrated into Cppless. A lot of the code that is written for the AWS dispatcher can also be reused, and thus implementing support for others shouldn't be too difficult. What does single source model exactly mean? I think this is best explained through an example. This is how we would traditionally utilize offloading to accelerate a task. Here we would have to write two different programs. Once we would have to write the Lambda handler, which receives Lambda invocations from the AWS runtime, then passes the request somehow, does something with it, and then returns a response, which has to be serialized once again. Furthermore, we have to write a client which creates invocations. We have to serialize the request, have to wait for the response. We have to mash up the function names on both sides. And in general, we have a rather loose interface between the client and the server. This makes it very cumbersome to accelerate and offload work using serverless functions in C++. This, on the other hand, would be how that same code would look like with Cppless. We assume that pi estimate is a function which performs a Monte Carlo approximation with n iterations, returning the result. And we can, of course, see that this is a problem well suited for parallelization. In order to offload the work to AWS Lambda, we first create a function provide abstraction. This is something that we call a dispatcher, a minimal platform-independent abstraction over a cloud provider. Next, we wrap the pi estimate function into a Lambda. This is necessary because tasks can only be created from types and not from raw function pointers. This Lambda can then be used to dispatch task invocations, instances of tasks with specific parameters. We also specify a location for the return value, a reference to a cell in an std vector in this case. Once the task invocations are dispatched, we wait for all the tasks to complete. Once we can be sure that all the results are written into the std vector, we can merge the result together. This simple example demonstrates the basic concept. The serverless function and the code which interacts with that function are defined in the same code base, making offloading transparent and natural. The glue code that would normally be necessary, serialization, uploading the deployment package, and creating invocations, is all replaced by the framework and managed internally. The idea of single source programming models for offloading is not new. For GPUs, CUDA and SQL already provide single source programming models. For serverless functions, on the other hand, we have implementations only in other programming language. Usually the general idea is the following. The dispatch function inspects the bytecode of the function at runtime. This is well defined in Python and Java, and ships that bytecode to a serverless function, which has a Python or Java interpreter loaded. This increases runtime overhead. The framework has to analyze dependencies and serialize constants. For C++, a high-performant system-level programming language, this is not ideal. We want to minimize that overhead. Ahead-of-time compiled programming languages also pose additional challenges. The architecture and operating system might differ between the host and the target platform. This implies the need for at least 2 different compilation flows. The glue code also depends on the function signature. In Java and Python, the contents of objects passed to invocations can be inspected at runtime, but in C++, this information is simply missing. Cppless thus tries to do as much work as possible at compile time, compiling the code for the serverless function, creating the deployment package, uploading it, assigning it a unique identifier. These are all steps that can be done at compile time and which reduce the overhead that is incurred at runtime. Let's go over the internal design of Cppless a bit. On the left-hand side, we have some C++-like pseudocode, which is similar to how Cppless is used. There's a function foo, which offloads invocations to bar through a task that we call bus. By explicitly instantiating the task type with the capture types on the right-hand side, we create a unique task type for this lambda. The task type is special in some way, and we'll walk through some details in a minute. This compilation unit is now compiled twice, once using a regular Clang invocation for the host system, and once with a different Clang invocation which outputs an executable for this specific task type. Along with the code itself, we can also define some metadata that is emitted by the compiler. This separate executable can then be turned into a deployment package by a deployment script, which subsequently can upload that deployment package to the serverless environment. Everything up to this point happened at compile time and is managed by the CMake integration. When we now want to execute a.out on the host, the identifier of the task is computed and the client connects to the serverless environment and invokes the serverless function through the cloud provider interface. The result is then serialized in the serverless function and sent back to the host. So how exactly was that task type that we saw in the previous example special? It is the generic task type defines something that we call alternative entry point, a concept that we are introducing. Alternative entry points are special functions or methods annotated with an entry point attribute as seen here. Normal C++ programs have one single entry point, the main function. It gets arguments from the operating system and is where the execution seems to start from a user's perspective. Alternative entry points exist in addition to the main entry point and are replacements to the main entry points to some extent. They get the same arguments from the operating system, but they can execute different code. Each entry point results in a separate executable. The main entry point results in the main executable, and the alternative entry points are compiled into alternative executables. These alternative executables can also, the alternative entry points can also be static methods of a class, and the templated task class has exactly such a static method. Thus, each instantiation of the task template results in a separate executable. In detail, this is what the output of the modified Clang invocation looks like. res.out is the main executable, res-alt-0.out is the alternative executable. The compiler also emits a manifest file, which stores metadata about the alternative entry point that were emitted. Here we can look up information such as the mangled name of the function which the alternative end executable was emitted for. But we can also add additional metadata as long as that metadata can be generated at compile time. This collection of output files can then be used in a deployment script to create the respective function or on the serverless provider side using their API. The metadata in the manifest file can also be used to generate a unique identifier and can also determine configuration parameters such as memory limits, CPU limits, and timeouts. The output of the host platform isn't special in any way in regards to the alternative entry point. The compiler simply ignores the flag and produces a single executable. We also have additional language extensions that are required to make offloading work as transparent as possible. Serialization is done through an open source solution called Serial. Serial already provides support for most standard library container types and provides support for archiving to different transport types. At the moment, we are using binary archive, but we also provide support for JSON. A requirement for Cppless was the usage of lambda expressions, but sadly, there's no reflection interface in C++ right now with which we can serialize and deserialize capture types. Thus, we have to introduce a lightweight compile time reflection interface that provides access to the capture types. Another challenge was posed by the generation of unique function identifiers. The two different compilation processes are separate, but at the end, they have to come up with a matching identifier at both stages in the pipeline. When deploying a function, we need to give it a name, and at runtime, we need to come up with the same name in order to create an invocation for that function. We can't solely rely on the traditional mangling process here, because the mangling identifiers might be different for the different platforms. And thus, we had to come up with a custom scheme. For Cppless, for the reference implementation we have right now, we use a modified version of the Itanium mangling scheme, which ensures that the identifiers match up. We currently provide two interfaces with Cppless: a low-level interface, which barely abstracts away the details of the cloud provider implementation, and a high-level graph implementation. Let's take a look at the dispatcher implementation first, which we saw in the first example. The dispatcher is an environment-specific class which exposes a common interface. Here we have an AWS Lambda Beast dispatcher, which dispatches tasks and locations to AWS Lambda using the Beast HTTP library. Specifically here, we have a dispatcher which defaults constructs from the environment. There are also some template parameters which we can set to determine how the data is serialized, but we'll just leave the settings at their default value. Once a dispatcher is created, we can use it to create instances of that dispatcher, which act like namespaces. This distinction is very essential, as dispatchers themselves should be serializable and thus can be transferred into a task, whereas dispatcher instances might make use of operating system handles and can thus not be serialized. Tasks can be derived from the original dispatcher interface, and we need to provide serialization and identification methods. We provide generic implementations based upon the Lambda, normal C++ Lambdas, which here is created internally in Cppless dispatch. We can also tell Cppless dispatch to create a task with different internal settings, modifying, for example, the memory limit or the timeout that the internal task should have. The two dispatch calls that we have here are instantiated with the same capture type from T, and thus only a single task and only a single AWS Lambda will be created. The dispatch method just starts the invocation, and an ID is returned with which we can identify the invocation. We can wait for tasks to complete using Cppless wait, or using an internal method. Here we simply wait for both tasks to finish. Once the wait call finishes execution, we can read the result from A and B. We also provide this high-level graph interface as an example of how to build high-level interfaces on top of dispatchers. The graph simply consists of nodes, which represent execution in some sense, and edges, which represent data transfer between different nodes. The graph interface can be used by building an executor, and then we can create something that we call a graph builder. Two types of nodes are currently supported: source nodes, which can be created using the schedule function, and which finish execution immediately and can be used as entry points into the task graph. Furthermore, we have task nodes, which take an arbitrary number of tasks as input, waits for all tasks to complete, and feeds the result into a lambda that the user can specify. The result of the task node is then the result of that lambda. Value handles can be extracted using the future method of senders, which are returned once we awaited for the executor to finish execution. This would be the next thing to do, calling builder.awaitAll once we constructed the complete task graph. Right now, we only implement one executor, one that we call the host controller executor, which internally uses a dispatcher to execute tasks, but we think that there's the opportunity to write customized executors, which make use of specific interfaces of cloud providers, such as block storage or pub subsystems, to get more efficient at executing task graphs. Implementation-wise, we implemented all language extensions as direct modifications to the Clang compiler, and they can be activated through feature flags, and this process can be further customized through additional flags. Activating the Cppless mode also enables ID generation function and sets a feature detection macro. The user space library is implemented in a separate GitHub repository and is currently a header-only library. We evaluated the performance of the framework using 6 different benchmarks and 2 micro benchmarks, and we'll go over some results. Most benchmarks will be self-explanatory, but I quickly go through them to explain how Cppless was used to speed up computation. The Fibonacci benchmark is rather simple. It simply calls lambda functions recursively, demonstrating the use of lambda recursion. Floor plan, Knapsack, and Greens are derived from the BOTS set of benchmarks and use their respective parallelization methods. You're right, we also have a modified version of a CPU ray tracer, which breaks down the image into small little squares, which are then rendered on the lambda invocations. We also have the very simple example of pi estimation using Monte Carlo methods, as we have seen in the first example. For the Queen's benchmark, we achieve very good scaling and only slightly increased overhead with increased task count. The major limiting factor, what we have found out, is waiting for the longest task due to the slight heterogeneity of the workload. This was also observed by prior work in this area. For the pi estimation benchmark, which is basically the best case scenario for our framework, we achieve near perfect scaling due to the uniform task length and an embarrassingly parallel implementation. We also had to notice some limitations of the framework though. And here in the Knapsack 40 benchmark, where we compute prefixes of the Knapsack and then send them to serverless executors, we only achieve a rather mediocre speedup, even with a lot of parallelism. Simulations confirmed that the branch and bound implementation that we use here scales badly as the result of limitations of the request response model. And we need to implement further communication patterns to improve performance upon this current state. The CPU raycasting benchmark is mainly limited by data movement, where we have to send the scene graph to the Lambda invocation and receive the image as a response. At 1000 tasks, this serialization overhead becomes noticeable, leading actually to a decreased speedup. This means that if many short tasks are required, we have to handle serialization with special care. And we could observe that optimizing the serialization can actually increase speedup in this example. Another major factor for this suboptimal speedup is, once again, the heterogeneous work distribution. Although the mean task time scales almost optimally, the maximum scales very badly. And we believe that to be the case, as the small regions in the image are much more computationally expensive than others. Although the speedup might be suboptimal, the overhead added at the cloud provider is statistically insignificant, and the cost, which directly correlates to memory gigabyte seconds, which we have plotted right here, stays almost constant. We can thus conclude that the overhead is dominated by algorithmic restrictions, not by Cppless itself. Furthermore, we did some experiments for the compilation time, and the compilation time seems to be dominated by the optimizer, and thus the required time scales linearly with the number of alternative entry points in a compilation unit. We believe that this compilation time can be brought down drastically by further deeper integration into LLVM. We see that there are multiple areas of further work that can be explored further. One of that would be independent executions. The current graph executor, which uses the host for communication, is quite limited as the host quickly becomes the bottleneck. And we think that the that custom serverless provider mechanisms can be used to transfer data between tasks more effectively. Furthermore, we would like to explore advanced communication patterns, allowing point-to-point communications between tasks, and something like a channel-like abstraction could also be used to implement synchronization primitives. To conclude the presentation, the Cppless compilation architecture with its language extensions allows for elegant compile-time definitions of serverless functions. The overhead incurred by the framework is only significant if many small tasks are dispatched or if each task requires a large amount of data. For trivial tasks, the overhead is around 1 millisecond and increases as more data needs to be serialized. However, the request-response communication model that Cppless is currently limited to severely restricts the algorithms which can be accelerated effectively. That was it from my side. Thank you for listening.